In week 1, we looked at how to scale vectors. What we're going to do now is look at how to scale matrices. It would be very tempting to simply tell you how to do this in practice. What we're going to do instead is we're going to look at how scaling a matrix is related to a linear transformation. So let's look at scaling a matrix. The way we're going to introduce the scaling of a matrix is that we're going to start by looking at a scalar beta and a linear transformation L sub A that takes a vector of size 3 and maps it to a vector of size 2. We then also define a vector function, which we don't know yet whether it's a linear transformation, and that vector function also maps a vector of size 3 to a vector of size 2. And the way it's defined is if you put in a vector x, the way you compute L sub b of x is to take that same x and plug it into the linear transformation L sub a, and then multiplying the result vector by beta. And notice that you know how to multiply a vector by beta. That's just a matter of multiplying the individual components by beta. And therefore, if we know what L sub a is, we know how to evaluate that. Now notice that L sub a is a linear transformation. Therefore, we know there's a matrix A associated with it. And we know, therefore, that L sub b of x can be computed as that matrix A times the vector x, and then the result of that multiplied by beta. For this particular example, in goes a vector. You take that vector, you put it into the linear transformation L sub a, result is multiplied by beta. And the question now becomes, is this a linear transformation? And if it is, what matrix represents it? And as we have been doing all along, what we're going to do is compute a matrix that might represent it, and then we're going to use that to see whether L sub b actually is a linear transformation. Now, in this particular case, we have a linear transformation A, and we know that it can be represented by a matrix A. And we know that that matrix must be 2 by 3 because the linear transformation starts with a vector of size 3 and outputs a vector of size 2. So let's just say that this is our matrix A. We're exposing the elements of matrix A. The question now is, can we come up with a matrix that might represent L sub b in terms of the elements of A? Well, let's have a look. Remember, what you do is you put in the first unit basis vector and you see what it evaluates to. Well, what we have to do is plug that into L sub a and then multiply the result by beta. But we know how to evaluate this. This is just equal to the first column of A. That's how the matrix A was defined. So we get this right here. But now we have a scalar times a vector, and therefore we know how to do that. Similarly, in goes the second unit basis vector, which means we have to plug it into L sub a. And that evaluates to the second column of A, multiplied by the scalar beta. In goes the third unit basis vector, and we find that all we have to do is multiply the third column of A by beta. What do we know now? If we know matrix A, then we know how to compute the columns of matrix B, which may represent the linear transformation L sub b. Okay, that matrix is simply this for the first column, that for the second column, and that for the third column. And lo and behold, notice that what that means is that we simply multiply the elements of matrix A by beta. Let's see if that matrix actually does represent L sub b. Well, if you work it out, you get this right here, and then that. Okay? All we did here was we exposed the components of x, plugged the vector x into L sub a, We know that that's the same as A times X, so we get this. We know how to multiply a matrix times a vector. That gives us this. And then this is just a vector, and we know how to scale a vector. That gives us this. But then we can distribute beta, and that gives us that. And then we can recognize that this is the same as this matrix vector multiplication, and therefore we see that this matrix indeed does represent the linear transformation L sub b. And then you can say, oh, but if we started with beta times this matrix times this vector, so this is beta times A times X, then we can ask the question, what matrix comes from multiplying A by the scalar beta? And what we see is that that's this matrix right here. So we're going to let you do this more generally in a homework exercise. A scalar times a matrix simply means that you take the individual elements of the matrix and you scale them by the scalar. And what it means is that if you think of doing beta times A times X, that's the same as beta times the matrix times the vector X. That's the same as multiplying everything out. And that's the same as multiplying the matrix times the scaled vector X. What we conclude from that is that beta times A times X is the same as A times beta X. And what that really means is that we can drop the parentheses altogether, because in what order you do the computation doesn't matter. You can first do beta times A and then multiply it times X. So you can first do beta times A and then multiply it by X. Or you could do beta times AX. Or you can actually move the scalar along and say A times beta X, where you first multiply X by beta. Let's have a look at an algorithm that scales a matrix by a scalar beta. You've seen these enough that I can go through this pretty quickly. You partition, you expose, you update, you move on. You expose, you update, you move on. You expose, you update, you move on. You expose, you update, and you move on, and you're done. So in summary, taking a matrix and multiplying by a scalar is simply the same as multiplying the individual elements by beta. And you can do beta times AX, or you can put parentheses around it, or you can move your scalar around. All of those end up being the same.